Union Pacific was desperate to conquer a 1.14% mountain grade with a single locomotive, hauling 3,600 tons where lesser engines failed. The engineers behind this feat created not just a giant, but a machine hiding breakthroughs, like the 4884 hinge that let 1.2 million pounds bend around 20-degree curves. The hidden story behind these features reshaped rail history. But what crisis forced such radical innovation, and how did one design decision rewrite the limits of steam power? Otto Jabelmann, head of Union Pacific's Research and Mechanical Standards Department, faced a freight crisis that could not be solved by bigger engines alone. The Wasatch Range, with its relentless 1.14% grade, had become a choke point for the railroad's busiest transcontinental route. Trains loaded with 3,600 tons of wartime freight stalled or crawled, burning through time and money as extra locomotives, so-called helpers, were lashed to their fronts. Each additional engine meant more crew, more coal, more water, and more delays. Company leadership demanded a single locomotive that could conquer the grade unassisted and keep freight moving fast enough to meet growing demands. Jabelmann's team calculated the numbers with precision. To haul 3,600 tons up that mountain, the new locomotive would need at least 135,000 pounds of tractive effort. But brute strength alone would not be enough. Curves on the Wasatch Line tightened to 20 degrees, sharp enough to derail anything too rigid or unwieldy. The solution would have to be powerful, flexible, and reliable, all at once. In 1940, Union Pacific issued a design brief to the American locomotive company Alco, with specifications that read more like a challenge than an order. The mandate was to build 25 locomotives, each able to replace double heading on the mountain, each capable of moving 3,600 tons over the 1.14% grade without a helper. The contract's urgency was clear. Wartime traffic was surging, and every day lost to inefficiency cost the railroad both money and reputation. Jabelmann drove the process relentlessly, working with Alco's engineers to refine the design and ensure that the final machine would not just be the biggest, but the most capable ever to run on American rails. The order for 25 units was placed, setting in motion a project that would force every assumption about steam locomotive design to be re-examined. The need for mechanical flexibility, not just raw power, would shape every decision that followed. The big boy's defining secret wasn't just its size or power, it was the way its frame could bend to the will of the mountain. This flexibility made an enormous locomotive behave like a mountain goat on rails. At the heart of that capability sat a massive hinge, invisible beneath the boiler. The hinge let the front engine swing out up to 20 degrees on the sharpest curves of the Wasatch Line. Engineers did more than bolt two engines together. They shaped a three-point suspension system that distributed the locomotive's enormous weight, so every wheel stayed firmly on the rails, even as the front and rear engine units shifted independently. That suspension was critical to reliable operation. The 4884 layout became the signature of this approach: 4 leading wheels to guide the locomotive, 2 sets of 8 driving wheels split by the articulation joint, and 4 trailing wheels to support the firebox. The hinge relied on a wide, flat center casting, a steel saddle where the front frame could slide beneath the boiler, guided by polished brass surfaces. That sliding saddle allowed the locomotive to flex without twisting or binding, spreading the load across a wheelbase that, on a rigid frame, would have torn up the track at the first tight curve. The 4884 layout put power and flexibility together. Feeding the front engine with high-pressure steam required its own innovation. A spherical ball-joint coupling, engineered to maintain a perfect seal under 300 pounds per square inch, let steam flow from the boiler to the pivoting cylinders without interruption. The reach rods, long steel arms transmitting control from the cab, were pinned and bushed for both strength and flexibility, allowing the engineer to set the reverse gear on both engines with a single motion. Smart steam delivery kept both engine units working in concert. Equalization springs and careful weight balancing kept the big boy stable on uneven track, preventing any one axle from bearing too much force. This articulation system turned a 1.2 million pound locomotive into something nimble enough to snake through 20-degree curves, an engineering feat that made the impossible routine. At the core of the big boy's boiler was a design unlike anything else on American rails. It measured 107 inches across and stretched nearly the length of a city bus. It operated at 300 pounds per square inch, one of the highest pressures ever used on a steam locomotive. Inside, more than 5,800 square feet of evaporative surface and 2,466 square feet of superheater tubes transformed water into high-pressure steam at a rate that could rival a small power plant. Feeding this appetite required a firebox with a 150-square-foot grate, engineered to burn Wyoming's low-grade bituminous coal efficiently. A mechanical stoker, itself a marvel, delivered up to 12.5 tons of coal per hour from the tender, spreading it evenly across the immense firebed. This system was not just about brute force. It was about matching the region's abundant coal supply to the locomotive's needs, turning a local resource into reliable rolling energy. Every ton of coal and every gallon of water was converted into the relentless steam that powered both engine units, setting the stage for the big boy's legendary performance on the mountain grades. Every breath the big boy took was engineered for purpose. When its massive cylinders pushed spent steam upward, the blast did not just vanish into the sky, it pulled fresh air through the firebox, feeding combustion with relentless force. This was no accident. Alco's engineers fitted the locomotive with cast bronze nozzles, precisely shaped to drive a powerful draft up through twin smokestacks. Each stack worked in concert, tuned to the width of the boiler and the demands of the firebox, ensuring that every shovelful of coal burned hot and clean. The dual stacks were not for show. They balanced airflow across the enormous grate, preventing cold spots and wasted fuel. At full throttle, the exhaust system moved a staggering volume of air, creating a low-pressure zone in the smokebox that drew flames and gases through the tubes at speeds that rivaled a hurricane. The result could be heard for miles, a deep, rhythmic bark, the audible signature of forced draft and efficient firing. On the rails, this sound was not just music. It was proof that every ounce of steam, every pulse of pressure, was being converted into real-world pulling power and ironclad adhesion. Big Boy's numbers set it apart from anything else on the rails. At full throttle, each locomotive delivered a staggering 135,375 pounds of tractive effort, enough raw force to move a loaded freight train up the Wasatch Grade without help. The horsepower curve peaked between 6,300 and 7,000 drawbar horsepower at around 40 miles per hour, translating steam pressure into relentless forward motion. To keep those 16 driving wheels gripping the rails, engineers aimed for a factor of adhesion near 4.0, balancing weight and power to prevent wheel slip even on slick track. The 68-inch drivers, smaller than those of high-speed passenger engines, were chosen for maximum torque rather than speed. Stacked against its chief rival, the Chesapeake and Ohio H8 Allegheny, the Big Boy holds its own. The Allegheny could claim up to 7,500 horsepower, slightly more than Big Boy's best, but its design favored brute force for Appalachian coal drags, not the long, winding climbs of the Rockies. On paper, the numbers are close. In practice, Big Boy's combination of power, flexibility, and adhesion made it the undisputed champion of Western mountain railroading, turning theoretical statistics into real on-rail dominance. Inside the Big Boy's cab, the line between machine and crew vanished. The engineer and fireman faced a control panel crowded with valves, levers, and gauges, each demanding constant attention. The backhead was a maze, dozens of brass handles for steam, water, and air, everyone with a specific role in keeping the locomotive alive. The engineer adjusted the throttle and reverse gear, balancing power to both engine units through long reach rods and synchronizing the movement of 16 driving wheels. Meanwhile, the fireman managed the mechanical stoker, watching the firebox temperature and coal feed rate, and adjusting water flow to match the boiler's appetite. Communication had to be wordless at times. Every whistle, every glance, every shift of a lever kept the Big Boy running at peak performance. Success depended on teamwork, discipline, and skill. For all its size and power, the locomotive was only as good as the people in the cab. In April 1943, Union Pacific put Big Boy to the ultimate test. On the steep Evanston subdivision, a single locomotive hauled 4,200 tons, 600 more than its design target, over the mountain grade, averaging 18 miles per hour. The numbers were staggering: 133 feet in length, 1.2 million pounds in operating weight, and a presence that dwarfed anything else on the rails. When diesel power swept across the industry, the age of steam giants ended. Yet 8 Big Boys survived, preserved as monuments to engineering ambition. In 2019, after years of painstaking restoration led by Ed Dickens and his team, Locomotive 4014 thundered back to life. Now the world's largest operating steam engine, it stands as living proof that the Big Boy's achievements endure, undiminished by time. Today, engineers face new frontiers, yet the ingenuity behind Big Boy still inspires solutions to outsized challenges. As railways adapt to automation and efficiency, the lesson endures. Bold design can reshape what is possible. The hidden genius of yesterday's machines keeps pushing the limits of tomorrow's progress. What do you think endures most?